Thank you very much. It's a great pleasure to be here. It's absolutely amazing to see so many people come out on a Thursday afternoon to hear a lecture about physics. It really warms my heart to see so many people here. This, I hope, is going to be an exciting lecture. And for those of you who are sitting on the steps in the center on either side, you might want to think about where you're going to go when I come into the steps, because for you it will be much more exciting than you planned on if you're sitting on the steps when I walk up there. So be thinking about how you're going to stand up and move, okay? So, well, we don't need that. We need this. That's not right at all. What the devil is going on here? This is the wrong presentation. You know, I had the right presentation when we started. You know, this is always the way it is. Everything works perfectly in practice. And here we go, Innsbruck. How did that get there? Okay, Innsbruck version 4. Okay. Okay, there we go. Wonderful. So, time, Einstein, and the coolest stuff in the universe. And of course, what we're celebrating is ICOKI, the 10-year anniversary of this wonderful institute here in Innsbruck, Austria. And one of the reasons I'm so pleased to be here in Austria to share this anniversary with you is that Austria is the birthplace of a lot of really wonderful physicists. And here is just a sampling of some of the awesome Austrian physicists who have changed the way we think about science. Boltzmann started us thinking about statistical mechanics. Of course, Schrödinger's equation is at the heart of quantum mechanics, which has changed so many things. Pauli's exclusion principle is the thing that explains so much about chemistry and about the nature of materials. Lise Meitner was the one who discovered fission. But my favorite up here is one that you might not have heard of, Otto Frisch, who is the nephew of Lise Meitner. And the reason I like Otto Frisch so much is he was the first one that showed that you could push atoms around with light, many, many years before there were even lasers. And that is the basis of what my career has been about, is pushing atoms around with light. And so I'm really happy about being in the homeland of Otto Frisch. But that's not all. You may not know that Einstein was an Austrian citizen for a year or so, for technical reasons that I'm not entirely sure about. But I think that even the mountains are taking great pleasure in claiming Einstein as an Austrian. So, but there's even more. And the real reason that I'm so pleased to be here is not so much the historical set of awesome physicists, but the awesome physicists of today. This institute has a wonderful set of people. These are the scientific directors of this institute. And just last week, there's a new scientific director as part of this institute. And the work that's being done here in Austria is inspiring and guiding not only my own work, but the work of physicists all over the world. And so it's really wonderful for me to be here. So now, time, Einstein, and the coolest stuff in the universe. So what does time have to do with Einstein? Well, Time put Einstein on the cover of their magazine as the person of the century. And I think it was a pretty good choice, because Einstein changed the way we think about so many things, and changed the way his explanation of the photoelectric effect, for which he got the Nobel Prize, was the beginning of the idea that things can be both waves and particles at the same time. Stimulated emission allowed us to make lasers many, many years later. Brownian motion was the thing that convinced most people that matter is made up of atoms and molecules. Can you imagine that at the beginning of the 20th century, this was not a settled question, that, that matter is made up of atoms and molecules, and Einstein's understanding of Brownian motion was the thing that finally convinced the doubters. But probably the thing that Einstein is most famous for is his theory of special relativity. Special relativity changed the way we think about space and time. The vice rector was telling you about a number of people who have changed our paradigms for the way we think about ourselves. Einstein changed the way we think about the stage on which we act out our lives. In fact, before Einstein, people thought that time and space was exactly that, a stage like this one, an unchanging platform on which the events of life take place. But what Einstein showed us was that the stage was part of the action, that it would change depending upon what was happening and depending upon who was looking at it. And one of the things that Einstein taught us was about the relativity of time. And the way he came to his conclusions about the relativity of time was asking himself a question that people have probably been asking themselves since the beginning of recorded time. What is time? What is this strange thing that is always in the present but will soon become the past and that will move into the future? What is this thing that we call time? And Einstein gave an answer to this question, which you may find to be a bit superficial. He said that time is what a clock measures. Now that may seem to be a silly answer, but in fact, by taking seriously the idea that time is what a clock measures, and by thinking about what happens when different people look at the same clock, he was able to come to his understanding of the relativity of time. But if time is what a clock measures, then we may ask ourselves, what is a clock? Well, there are many different kinds of clocks, and for me, a clock is something that ticks, something that gives us a regular series of events. The oldest clock is the Earth. The rotating Earth makes the sun appear to rise and set, and so primitive people were able to tick off days and seasons by watching the periodic events of the rising sun and the changing of the seasons. As things got more sophisticated, people, in fact it was Galileo, according to legend, who while sitting in the cathedral in Pisa one day was watching the chandelier swing back and forth and timing it with his pulse. Apparently he wasn't paying very much attention to the worship service that was going on. And timing the swinging of the pendulum with his pulse, he was able to determine that according to the legend, that the period of the pendulum was independent of how far the chandelier was swinging. And that meant that the pendulum became a good ticker for a clock that people like Huygens made. And here's an example of a beautiful tall clock or grandfather's clock that is often made using this kind of a ticker, a swinging pendulum. Some of you may be wearing a quartz watch. Inside that quartz watch, there is a tuning fork-shaped quartz crystal, and the vibration of that quartz crystal is the ticker for that watch. There are many different kinds of clocks, and some of these clocks are not only marvels of engineering, they're works of art. Here is one that you may be familiar with. But every one of these clocks are imperfect in one way or another. The length of a pendulum may stretch or shrink, and that will change its period. Every quartz crystal is a little different from every other one, and so every watch keeps time a little differently, and it may change depending upon whether you wear the watch on your wrist or whether you keep it on the bedside stand. Even the rotation of the Earth is not constant. It is slowed by the tides, and it is changed by changing ocean currents and earthquakes and tsunamis. The fact that the Earth is not a constant timekeeper was something that was made clear to me in a rather dramatic way one day when I was visiting the U.S. Naval Observatory. Now, like the navies of all countries, the U.S. Navy is interested in timekeeping because timekeeping helps them learn where their ships are on the open sea. And they have wonderful clocks at the U.S. Naval Observatory, and I was visiting a colleague who was going to show me some of the latest clocks. And as we were walking along the corridor, we passed by an office on which it was written, Director of Earth Rotation. Sounds like a very responsible job. You wonder what happens if that guy goes on vacation. Well, the point is that somebody keeps track of the ways in which the rotation of the Earth vary compared to more stable clocks than even the Earth. And what are those more stable clocks? Those more stable clocks are atomic clocks, because atoms are the best tickers. Why do atoms tick? Because there are energy levels in the atom, and the frequency that corresponds to the difference between those energy levels can be used as the ticking for a clock. And the wonderful thing about atoms is that every atom of the same kind is absolutely identical to every other atom of the same kind in the entire universe, as far as we know. As it turns out, we define time to be a certain number of ticks of the cesium atom. Cesium is over here on the periodic chart that you can see on the right-hand side of the lecture hall. And I can see Ben hiding his eyes, imagining that I'm doing terrible things by shining a laser pointer over in that direction, probably violating all sorts of safety regulations. But we're here to have fun, right? And as far as we know, every cesium atom in the entire universe is identical to every other cesium atom in the universe. And that means that if you make a clock based on the ticking of the cesium atom, then that clock will keep the same time as the clock of anyone else who makes a clock based on the cesium atom. So atoms are the best clocks. Well, how good are these clocks? Well, for less than 100 euros, you can certainly buy a quartz watch that is good to about a few seconds a month, 30 seconds a year, a part in a million, okay? This is amazing that you can buy for such a little amount of money a scientific instrument, a clock, that is better than a part in a million for just a few $100s. But if you're willing to spend 100,000 euros, you can buy an atomic clock that is good to a part in 10 to the 12, a part in a million, which is 30 seconds in a million years. Now you may say $100,000. That's a lot of money, but think about it this way. You spend 1,000 times more money and you get 1,000,000 times better performance. To me, this seems like a real bargain. But you still might ask yourself, why does anyone need a clock that is that good? I mean, after all, we don't need to know what time it is to that level of accuracy in order to go about our daily lives. Or so you may think. In fact, I hope to convince you that you are very happy for things in your daily life that somebody knows what time it is to that level of precision. I found this advertisement in a magazine one time. It said, if you get into trouble in this car, don't worry, because help is only 10,000 miles away. And the 10,000 miles that is referred to is the orbiting altitude of a constellation of satellites that make up the satellite navigation system, the GPS system. And what does that GPS system consist of? Here's a cartoon of one of those GPS satellites. Every one of those satellites has on it several atomic clocks that are keeping time at the precision that you could buy on Earth for $100,000. If you want to put one of those things in a satellite, it's going to cost you a lot more than $100,000, because the space qualification that they have to do in order to put something in a satellite is really quite rigorous. But that's the point. It's that kind of quality. So clocks that are good to a part in a million. How does this work? Well, imagine that you've got two satellites in view, and they have atomic clocks on board that are synchronized with one another from the ground, and you also have a clock. in your GPS receiver. Now, in fact, your GPS receiver does not have such a clock in it, but let's imagine, for the sake of argument, that you do have a clock in your GPS receiver, and they're all synchronized. So you can now see that all of those clocks are reading 1 right now, at some instant in time. Now, let's broadcast from the satellites what time it is. And we're also going to broadcast from the satellites where they are. It takes some time for the information about what time it is to get to your receiver. So when you receive that the satellite thinks that the time is 1 and your clock says that it's 4, that means you know how far away the satellite is because you know how fast light travels and how fast the radio signals travel. So you know how far you are away from that satellite, which means you know you're somewhere on this circle. Well, there are more than one satellite. And when you get information from 2 satellites, then you know how far you are from 2 satellites. And remember, you know where those satellites are. If you know how far away you are from 2 things on a plane, and you know where those 2 things are, you know where you are. It's at the intersection of this circle. You can probably figure out it's not up here. Now, of course, we don't live in a 2-dimensional universe. We live in a 3-dimensional world, so you need 3 satellites. And remember, you don't have a clock in your GPS receiver, so we need a 4th satellite. That becomes your clock, the extra piece of information you need. So whenever you look at your GPS receiver and it says acquiring satellites or whatever it says, it's trying to find 4 satellites. As soon as it can find 4 satellites, it can tell where you are anywhere on the face of the Earth to within a few meters. And it all happens because we have atomic clocks. And we are now using these kinds of systems to put in our cars, our taxis. The taxi that took me to the labs yesterday had a GPS in it. Commercial aircraft, ships, golfers use it to find out how far they are away from the hole. And scientists use it to study continental drift. All sorts of things that are the kinds of things we can appreciate for our daily lives depend upon the fact that we have atomic clocks. And those atomic clocks are really good. So now you might want to ask yourself, what do these atomic clocks look like? Well, there was another advertisement that I found in a magazine. It said that recently scientists in Braunschweig, Germany, they were referring to the PTB, the Physikalische Technische Bundesanstalt, the equivalent of NIST in Germany, where they have atomic clocks just like we do. And they said they'd set the atomic clock back 1 full second. This is true. Every once in a while, whenever atomic time gets out of sync with solar time, with Earth time, they set the time off by 1 second so that they don't get too far away from each other. This is true. And then they claim that their flight schedules were adjusted accordingly. Yeah, right. This airline is no longer in business, as I remember. But that's not the point. The point of this whole thing, well, actually, in order so you get a proper appreciation of what the point of me bringing this up, I want to ask my friend Max to tell you what is the point of all of this. So Max, would you come up and explain to everyone why I'm showing this picture?
Das Gerät, vor dem diese beiden lächerlichen Clowns stehen, sieht überhaupt nicht wie ein echter Domo aus.
Exactly. This thing is nothing like an atomic clock. And isn't it delicious how ridiculous these 2 clowns look? You see this little model of an atom up here? Isn't that wonderful? If you were to come to our laboratories in Boulder, Colorado, or go to an atomic clock laboratory anywhere else a few years ago, you might see an instrument that instead looks a little bit like this. So the question is, what is inside this long tube where the guts of the atomic clock reside? Well, here is a simplified schematic of what is inside there. We have an oven. The oven has some cesium metal. Remember cesium over here on the periodic chart on the right-hand side? Cesium will burn in air, but this is all done in a vacuum, so we don't have to worry about that. You heat the oven up, you vaporize the cesium, and a stream of cesium atoms come out. We call it an atomic beam. Comes out in a stream moving at a little bit more than 100 meters per second, almost the speed of sound. These cesium atoms are going along. And what we do is we first start with the cesium atoms in one particular energy state, and we shine microwave radiation onto them. And when that radiation has just the right frequency that corresponds to the difference between two of these energy levels, then the atom will flip its, what energy level it's in, and then you can tell by doing an analysis of the atoms over here whether they've changed their state. And it's only when the frequency is just right that the atoms will change their state. And that way, when you've got this microwave frequency tuned just right, it becomes a clock that you can then broadcast and tell everybody what the ticking rate is. The best of these clocks are accurate to better than a part in 10 to the 14. That means better than a part in 100 million million. But this kind of clock can't get any better because the atoms are moving so fast. First of all, you can imagine that if you don't have very long time to measure what's going on, you won't be able to do a very good job. Somebody said making an atomic clock is sort of like trying to tell time from a clock that is whizzing past you at the speed of sound and then crashing into the wall. That doesn't sound like a very easy thing to do, but people have been working on this for over 50 years and have gotten this good, a part in 100 million million. But that's as good as they can get. And there are other problems, Doppler shifts, relativistic effects, that make it impossible to make these clocks do any better. And so in order to do better, and that's always what we want to do at a place like the National Institute of Standards and Technology, we keep standards. And we want to do better. And in order to do better, what we have to do is make the atoms move more slowly. And in order to make the atoms move more slowly, we have to cool them down. And in order to cool them down, well, let me give you an impression of what we're going to do, of how cold we're going to make these atoms. So I think now we need the lights on in the front. So here, courtesy of my friends here in Innsbruck, I have a bucket full of really, really cold stuff. In here is liquid nitrogen. Maybe you should stand up. In here is liquid nitrogen. Liquid nitrogen, nitrogen is the main constituent of the air. So this is like liquid air. This stuff is so cold that compared to it, the floor is burning hot. Imagine what would happen if you were to pour cold water onto a red-hot stove. It would boil, and that's what's happening here. The liquid nitrogen is boiling because the floor is so hot compared to the liquid nitrogen. Now, if you've got something that's that cold, it seems like it might be a really good idea to use it to cool down a gas that you would want to make the atoms and molecules move more slowly. So here I have another bucket of liquid nitrogen, and I'm going to use a traditional container for hot gas. I don't know if you have the expression hot air. I'm from Washington, D.C., and hot air is what the politicians create. So we have a container full of hot air, and we're going to put it into this bucket full of liquid nitrogen to cool the air down to make the atoms and molecules move more slowly. So we'll put that in. Wonderful, wonderful. Okay. Let me just put a little bit more in here. Okay, so what else can I do to show you how cold this stuff is? Here is what we call a Dewar flask. Some people call this a thermos bottle. It's a very well insulated container, and but it's been sitting out at room temperature all day. So that means that compared to the liquid nitrogen, this container is burning hot. Imagine that you took a metal bucket and put it into a fire and heated it up until it was red hot, and then took cold water and poured it into the metal bucket. What do you think would happen? Well, what would happen is that it boils over, and that's what's happening here. Don't try this at home. Okay, so it's boiling away, cooling down the inside of that container. So while it's doing that, let's cool down some more gas. So we put a red balloon in, right? So we'll put a white one in for the Tyrolean colors. Because of course we want to have lots of cold gas if we're going to do something with it. We want to have plenty. So let's put some more cold gas into the liquid nitrogen to cool it down. Okay, so now I look into here and I see that the boiling has subsided. That means that the inside of the Dewar has cooled down, but a lot of it's boiled off. So I'm going to pour a little bit more in to top it up. Okay, now, here we have a nice fresh flower. Nice fresh flower. Just picked up last night, all right? Been kept in water all day, nice fresh flower. At room temperature, compared to the liquid nitrogen, this thing is red hot. In fact, it's even red. Imagine that you took a metal rod and heated it up in a fireplace until the metal rod was glowing red, and then took the metal rod out and plunged it into a bucket of cold water. What would happen? The water would boil. And that's what's happening to the liquid nitrogen. It's boiling. Well, the flour is making the liquid nitrogen boil. So it's boiling away. And while it's boiling away, let's cool down some more gas. What? We're going to stick with the Tyrolean colors here. Okay. Okay, fine. Now, let's see. Yes. Now, I'm sure that when you were learning how to do things in the kitchen, when you were young, that your mother explained to you that you should never ever take a closed container of liquid and put it into the oven. So here we have a container, and here we have a liquid. Let me just get things okay. Now, compared to the liquid in this container, this room is an oven. This is the garnish. Okay, so we'll see what happens there. And in the meantime, so how many balloons have I put in so far? Three. What colors? Okay, so the last one was red. Let's go with white again for the next one. Okay. Here we go. Wonderful, wonderful. Okay, now, let's see what has happened to the flour. I look in and I see that the boiling has subsided. That means the flour is now down to the temperature of the liquid nitrogen. This flour is frozen so hard that when I take it out, I can crush it like it was made out of glass. This stuff is really, really cold. And, you know, if you've got something that cold, then why not use it to cool down your gas to make the atoms and molecules move more slowly. You know what? I forgot to show this beautiful little video that shows the difference between hot and cold. Because the difference between hot and cold, you see, is, of course, how fast the atoms and molecules are moving. But you knew that. But you know, somebody spent a lot of time making that video. So I want to make sure that I show it. Okay, so we want to make our atoms and molecules move more slowly, because if the atoms and molecules move more slowly, then that means we'll be able to study them and to measure them better. Maybe I've made this one a little bit too big. I'm having a hard time fitting it in. Okay, we'll just have to force it a little bit and it'll go in. There we go. Okay, fine. Now, what else can I do to show you how incredibly cold this stuff is? So here I have a nice bouncy rubber ball, okay? And what we're going to do is we're going to take this rubber ball and put it into the liquid nitrogen, okay? Now, while we're waiting for that to cool down, let me take a rubber band. So nice stretchy rubber band, okay? Now, let me put the rubber band into the liquid nitrogen. Now, you can't see this, but what happens, anytime you put anything hot into the liquid nitrogen, it makes the liquid nitrogen boil. But the rubber band isn't very big, so it doesn't take very long before the boiling subsides, and I can take this out, and it is frozen so hard that I can snap it like it was a dry twig. But all I have to do is warm it up in my hands a little bit, and it's a nice stretchy rubber band again. This stuff is incredibly cold. And, you know, if you've got stuff that's that cold, then why not use it? Been doing this too much. Okay, we're going to stretch this one out a little bit. You know, the first 5 worked great. Okay. Whew. Okay, let's put another balloon in here. Okay, now let's have a look at the rubber ball. So I think we need the shield just in case. Just in case, let me show you. Remember how nice and bouncy the rubber ball was? It breaks like it was made out of porcelain. This stuff is really, really cold. And you know, if you've got something that cold, it seems quite reasonable that you should use it to cool down your gas. Now, how cold is this stuff? Well, to appreciate how cold it is, I have to tell you about the way that physicists like to measure temperatures. Now, typically we measure temperatures, the temperature of the air outside, we measure it on the Celsius scale. When it's cold out, it might be 0 Celsius. When it's really cold, and I understand it does get really cold in Innsbruck, it might be -10 or even -20 on a really cold day, right? Well, physicists don't like these minus numbers, so we use a different temperature scale where the lowest possible temperature you could have, even in principle, is 0. We call it absolute 0. And when the degrees are the same size as Celsius degrees, we call this the Kelvin scale. Room temperature on the Kelvin scale is about 300 degrees. Sounds pretty warm, doesn't it? And I think it feels pretty warm in here, doesn't it? Water freezes at about 273 Kelvin. Dry ice, some pretty cold stuff, has a temperature of about 195 degrees. The coldest temperature anybody has ever measured on the face of the Earth was someplace in Antarctica in the wintertime, 185 degrees above absolute 0. That's the coldest air temperature ever measured on the face of the Earth. Colder than dry ice. This stuff that is so cold that it boils when you pour it out on the ground. I think it's time for everybody who's sitting down to stand up. Because I'm not sure that everybody has seen just how cold this stuff is. You see how wonderful and how cold this stuff is? And this is amazing. This is amazingly cold. Let's go down this way. So everybody can see. This stuff is just wonderfully cold. Oh no, you're not getting away with anything either. This stuff, you know, if you have not worked or at least been in a low temperature physics laboratory, this is the coldest stuff you've ever seen. Do you know what its temperature is? 77 degrees above absolute 0. In fact, actually in Innsbruck, because we're up a little bit, it might be more like 76 degrees. Because, you know, things boil at a lower temperature when you're at high altitude. So this is probably, for most of you, the coldest. Wow! Wow! Fantastic. This, people, this is why your mother was right. You should never, ever put a closed container of liquid into an oven. And it just goes to show how incredibly cold the liquid nitrogen is compared to room temperature. And this incredibly cold stuff. And so it seems with something so incredibly cold, it makes perfect sense to use it to cool down your gas to make the atoms and molecules move more slowly. And that's what we were doing here. But some of you may have noticed that I was able to put more balloons in here than there seemed to be room for. And this is not because the air went out of the balloons, but because the air condensed in those balloons. These balloons are as flat as pancakes. Okay, so how many balloons did I put in there? Red and white, right? How many blue balloons did I put in? How about orange? How about green? Blue again. Even purple. So I could have kept putting balloons in until we got tired of it. What happened was, not that the air in those balloons went away. What happened was the air in those balloons condensed. The liquid nitrogen was so cold that it made the air turn into a liquid or a gas. And that's what you see here. If I take any container of gas and put it in contact with a refrigerator, then if the refrigerator is cold enough, then it will turn into a liquid or a gas, or the gas will, a liquid or a solid, or the atoms will stick to the sides of the container, and I will not have a gas anymore. Now, if I want to make an atomic clock, I want to have those atoms floating freely in space. I don't want those atoms stuck onto other atoms. I don't want those atoms stuck onto the inside of a balloon or the inside of any other container. I want the atoms to be floating freely in space so that their ticking frequency will be undisturbed. So how am I going to cool something down without touching it? I think we need to turn off the lights now on the front of the auditorium. How are we going to cool something without touching it? And the answer to that question has been staring at us from the heavens for centuries. Because since the time of Kepler, people have known that the tails of comets... Whoa, that was a balloon. Somehow or other, some liquid nitrogen got into that balloon, because when I threw it, I felt, oh, this one's really heavy. And so I threw it in front of the audience instead of into the audience, and so it made quite a pop when it finally broke. Coming back to comets, since the time of Kepler, people have known that the tails of comets always point away from the sun. So if you have a comet that's coming in from someplace out in the Oort cloud, and as it comes close to the sun, the tail will stream behind it. But as it goes around the sun and goes back out, then the tail will stream in front of it. Why is that? It's because, you know, we're not in third grade. This is what elementary school kids do, is bounce the balloon around, right? Just hang on to it, okay? The fact of the matter is, though, my favorite audience for giving talks like this is elementary school children. And do you know why? Because elementary school children have a wonderful and absolutely irrepressible sense of curiosity. When I pour liquid nitrogen on the floor in front of people like you, and I'm speaking just to the grown-ups here, you recoil. And if I pour liquid nitrogen on the floor in front of elementary school children, they're down on the floor on their hands and knees trying to see what is this wonderful stuff. And that kind of curiosity is what makes for a scientist. And in many respects, scientists are just children that never grew out of that childlike curiosity. Anyway, why do the tails of comets point away from the sun? Because the sunlight pushes on the dust and gas that make up the comet and push it out to make the tail. And that's the key thing. Light pushes on stuff. High temperature means that the atoms are moving around really fast. What we're going to do with laser cooling is to push on the atoms in such a way as to make them slow down, and that's equivalent to cooling them. That's how laser cooling works. Well, now the details of how laser cooling works. Here comes the physics. There's two things you have to understand how laser cooling works. One is that light will exert a force on atoms only when the atoms absorb the light. And unless the light is just the right color, it will not be absorbed by the atoms. This laser beam, green laser, I shine it through the air. The air does not absorb any of the light. That's why the light makes it to the screen, and that's why you can see me and one another, because the air does not absorb the light. But if I had a gas of, say, sodium atoms, and I shine just the right color of yellow light at it, then that gas of sodium atoms will absorb the light, and it will get a push in the direction in which the light is moving. The color has to be just right. Color is a manifestation of what the frequency of the light waves is. Light is just like radio waves and microwaves. It has a frequency. It's just a much higher frequency, almost 10 to the 15 cycles per second, 1,000 million cycles per second. And unless the frequency is just right, typically within 10 million cycles per second. That's something like within a part in 100 million. You have to get the color right to a part in 100 million for the atoms to absorb the light. If it's not that right color, the atoms won't absorb it. Now, you could never tell the difference between two beams of light that were different in color by a part in 100 million, but the atoms can tell because the atoms are so exquisitely sensitive to the color. So that's one thing to know. The other thing to know is the Doppler shift. If you are moving toward a source of waves, you will see the frequency of those waves be higher. Imagine that you were on the beach and waves were coming into the shore, and you could count how many waves came in a certain length of time. That would be the frequency of those waves. If you got into a boat and moved into the waves, you would see the waves hitting the front of your boat faster at a higher frequency. We call that the Doppler shift. It works for ocean waves, it works for sound waves, and it works for light waves. So if you're an atom moving toward a source of light, it will look like the frequency of the light is higher. Now you know what you need to know to understand how laser cooling works. So imagine that I have a laser beam coming from the left, and I have atoms, and the atoms in the gas are moving in every different direction. But we're going to simplify it and say some are moving to the right and some are moving to the left. Now, if I tune the frequency of the laser so that it is a little bit lower than the frequency that the atoms want to absorb, if I now think about this atom that's moving this way toward this laser beam, it will see the frequency of this laser Doppler shifted up so that it's closer to the frequency that the atom wants to absorb, and the atom will absorb the light and slow down. On the other hand, this atom that's moving away from the laser beam will see it Doppler shifted in the opposite direction. It was already too low, so this atom will not absorb the light very much and will not be speeded up very much. It would be speeded up if it absorbs it, but it doesn't absorb very much, so it doesn't get speeded up. So now you see we have some atoms are slowed down a lot, and some atoms are speeded up a little. So this sounds like a good start. But all we have to do is bring in light from the other side, and now you see this atom, the one that didn't have much happen to it before, now sees this laser beam as being the one that has the right frequency, and it absorbs the light and slows down. And this atom, going this way, sees this laser beam as having the right frequency, and it absorbs it and slows down. So no matter which way the atoms go, they always see that the laser beam that is opposing their motion is the one that can be absorbed preferentially, and therefore they slow down. Well, you can bring the laser beams in from top and bottom and backwards and forwards, and now no matter where the atoms go in 3 dimensions, they will, no matter what direction they go, they will feel a force that opposes their motion. When Steve Chu and his colleagues at Bell Labs, and I should say that I'm telling you this story about laser cooling, it was a story that played out in a number of laboratories around the world. When Steve Chu, in his laboratory at Bell Labs, did this for the first time, he realized that the atoms were experiencing what is very much like viscosity. If you were in a very viscous fluid, like a sugar solution like molasses, then no matter which way you moved, imagine you're in a swimming pool full of molasses, no matter which way you move, you would feel a force that opposed your motion. And the atoms feel the same way, and so Steve Chu called this optical molasses. Now, if that was all there was to the story, the atoms would simply come to rest. But that's not all there is to the story, and part of the reason why that's not the end of the story is because of what Einstein taught us in 1905, that we should think of light as being a stream of particles. So when the atom absorbs light, it absorbs it one particle, or one photon as we say now, at a time. So let's imagine that I'm an atom. And let's say that just by chance I happen to be at rest, and there are laser beams coming from one side and coming from the other, and they have the same frequency and the same intensity. It's equally likely that I will absorb a photon from that side or from that side. It's completely random which side I will absorb from. And when I absorb, let's say from that side, I get a kick. And now, because I got a kick from that photon, I'm moving, okay, at about 3 centimeters per second if I'm a sodium atom, but there's more. I'm excited, can't you tell? And that means that I'm in this excited state. I want to get rid of that energy, and I do it by shooting off a photon. And the photon is shot off in a random direction. And just like shooting a gun, you get a recoil, and you move differently by 3 centimeters per second, depending upon the direction. And now you're ready to absorb another photon, maybe from that side, and get a kick and start moving in this direction. So every time you absorb or emit a photon, you get a kick in a random direction. So the atom is doing this kind of a random dance every time it absorbs and emits a photon, and that heats the atom up. On the other hand, if the atom starts to move in one direction, then the Doppler effect guarantees that that motion will be damped, and then soon it will be moving in another direction. And so there's this balance between the heating effect of the randomness of the emission and absorption and the cooling effect that's enforced by the Doppler shift. And when you figure out what the balance is, you find out that the limit, the temperature limit that you can get to for sodium atoms is that you can get as low as 240 microdegrees above absolute zero. 240 microdegrees. Remember, people, this stuff, liquid nitrogen, which is so cold. Have you people over here seen this? What about you people on the steps? Have you seen how cold this is? This stuff boils when you pour it out on the ground. I promised exciting, didn't I? This stuff is amazing. And it's the coldest stuff most of you have ever seen. And this is 77 degrees above absolute zero. 77 degrees above absolute zero. We're talking about getting to 240 millionths of a degree. 1/4 of a thousandth of a degree above absolute zero by laser cooling. So you can bet that people got pretty interested in making things that cold. So people at Bell Labs, people in Paris, did these experiments. And here's a picture from our laboratory. What this is showing is 3 pairs of counterpropagating laser beams intersecting right here. That is a ball of sodium atoms about 1 centimeter across. And the atoms that are in that intersection of laser beams are having their motion so strongly damped by the laser light that they accumulate there. And we've got about 100 million atoms there. And the question is, how do you measure the temperature of something like that that is supposed to be as cold as 240 millionths of a degree above absolute zero? It's not like you can take a thermometer and stick it up in the atoms. So here's what Steve Chu devised as a method for measuring the temperature. He said you put the atoms into the optical molasses, and they're jiggling around like this, but not going very far. And now you want to see what is the random motion of those atoms, because that random motion is the temperature. You turn the laser beams off. Now there's nothing to change the velocity of the atoms. They just go flying off in all directions, and the hotter the gas is, the faster they will fly away. It just expands freely in a vacuum, as any gas would, and the hotter it is, the faster it expands. So a few milliseconds later, a few thousandths of a second later, you turn the laser beams back on, and the fraction of the atoms that are still in the intersection of the laser beams gives you a measure of how hot the atoms are. The smaller the fraction, the hotter the atoms are. So they did that, and they measured the temperature to be 240 microdegrees above absolute zero. This was wonderful because it was the coldest temperature that was predicted was possible. There was a big uncertainty because these experiments are difficult. And we repeated those experiments in our own laboratory using exactly the same method, and we got exactly the same result. And then we started to make other measurements to see if the way in which the cold gas behaved as we changed the intensity of the laser and the frequency of the laser, if it behaved the way we expected. And it did not. And we couldn't understand it. So we did more and more experiments, and finally we decided we would measure the temperature again. And when we measured the temperature again very carefully, we found that the temperatures were much colder than the theory predicted. And as Rudy explained, this is a wonderful thing. Of course, at the beginning, we didn't believe it. In fact, we felt an awful lot like the poor devils in this cartoon who have seen something that is much, much colder than should be possible for the environment that they're in. And so we had to repeat our experiments again and again, and we finally published a paper in which we showed from repeated measurements with different techniques, the temperature was not just a little colder, the temperature was 6 times colder. It was 40 millionths of a degree above absolute zero, when it should have been no colder than 240 millionths of a degree above absolute zero. So other people repeated those experiments and came to the same conclusion, that the temperature was very much colder than it should have been. So it's pretty clear now that the experiments were right and the theory was wrong. Well, this is what experimentalists love, is when they can show that the theorists are wrong. So that, of course, created a lot of discussion about what the nature of a new theory should be. And I wish I had time to explain to you, because the theory that came out of this was absolutely beautiful. And what could be better is that you find out that things were not the way you thought they were, and you find out the explanation for why they were not the way you thought they were is incredibly beautiful. But I don't have time. But guided by that theory, guided by that new theory, we were able to adjust things so that we got the temperature even colder. And by 1995, we had gotten the temperature of cesium atoms. Remember cesium, the one we use for clocks? The temperature of cesium atoms down to 700 nanokelvin. That was 200 times colder than it was expected you could get cesium atoms. This is 100 million times colder than liquid nitrogen. And liquid nitrogen is the coldest stuff you've ever seen. It boils when you pour it out on the ground. And we're getting things 100 million times colder than liquid nitrogen. The coldest natural temperature in the universe is the temperature of outer space. If you're far away from any planets or stars, the temperature of outer space, which is warmed by the leftover radiation from the Big Bang 14 billion years ago, that temperature is a little bit less than 3 degrees above absolute zero. So we are 4 million times colder than the coldest natural temperature in the universe. The velocity of atoms at this temperature, of cesium atoms at this temperature, is less than 1 centimeter per second. So now we've gone from a velocity that's almost the speed of sound, over 100 meters per second. Speed of sound is about 300 meters per second. So we have from over 100 meters per second to less than 1 centimeter per second. So what kind of a clock can we make with this? Well, the stat term is not going to get any better if you cool it down. But an atomic clock will get better if you cool it down. So let me remind you about what the atomic clock did. I had a stream of cesium atoms going along here, and the cesium atoms would stay in the apparatus for just milliseconds, because the length of the apparatus is about 1 meter, and they're going at a few 100 meters per second. So you would only have a few milliseconds to make the measurement. Now, the question is, what happens if instead of having atoms moving at 200 meters per second, I have atoms moving at just 1 centimeter per second? What kind of a clock can you make with that? And the answer is no clock at all, because the atoms fall like stones. Now, if you've got something that's moving at 1 centimeter per second and you let go of it, it's going to fall almost straight down. But there is a wonderful idea that was imagined over 50 years before by a guy named Gerald Zacharias. He said, get your slow atoms, and he didn't have any, but he imagined maybe you could get some slow atoms, and throw them up and wait for them to come back down. And so make your measurement from the time that you throw it up to the time it comes back down. And if you throw it up 1 meter, the same length that these clocks are in the laboratory, you just make it vertical, then it will come down after about 1 second. So instead of a few thousandths of a second, you have a whole second to make your measurement. Here is a picture from our atomic clock laboratories in Boulder, Colorado. That's Don Meekhoff and Steve Jeffords. And they cool cesium atoms down here at the bottom of this apparatus, and they shoot them up about 1 meter high, and they come up and they come back down, and they have a whole second to look at them. And these clocks, and clocks like them in other laboratories around the world, are the most accurate primary time standards that have ever been made. We call these things atomic fountain clocks because it's sort of like one of these jets of water that goes straight up and then comes back down in a fountain. And these clocks are now better than 1 part in 10 to the 16. That's better than 1 second in 300 million years. But that's just a start. Laser-cooled ions, which are one of the things that are being studied here in Innsbruck, have made clocks that are as good as 8 parts in 10 to the 18. And that's just a start. Using neutral atoms, people have gotten accuracy of even better than that, 6 times 10 to the minus 18, and stability as good as 1.6 in 10 to the 18. That is about 1 second in the age of the universe. This is one of the things that laser cooling has gotten us. But now you may ask yourself, now that you've got the coldest stuff in the universe, coldest by a long shot, what are you going to keep it in? I mean, what can you keep the coldest gas in the universe in? Imagine that this bowl is the container I want to keep my atoms in, and imagine that this ping pong ball is the atom. Well, first of all, we couldn't even imagine keeping these things in such a container when the atoms were hot. Because if the atoms were hot, they would just go right out of the bowl because the bowl wasn't deep enough. Now we've got the atoms really cold. We can hold them in a bowl, but if the bowl is cold, then the atoms will just stick to it, the same way the air stuck to the inside of the balloon. And if the bowl is hot, then that means the atoms inside the material of the bowl are jiggling around really fast. And if you put atoms in it, they will heat up the atoms, and you won't have cold atoms anymore. So you can't use a hot bowl. You can't use a cold bowl. You can't use any bowl at all that has any kind of material. Now we want to go to the document camera. So I think that is this, and we need the light on. Okay. One of the great things about magnets, do you remember the first time you held 2 magnets in your hand and turned them the right way and found that they pushed away from each other without touching? Wasn't that an amazing feeling? I still think it's amazing. So you can use magnets to push on other magnets without touching them. So the idea is that we can make a magnetic bottle, something that will hold atoms, because it turns out that our atoms are little tiny magnets. And we can use bigger magnets to hold on to our little tiny magnets. Let's go over to the video camera. Now, what we have here, as soon as we get the video camera on, so what I've got here is a big magnet. Inside this wooden case is a big magnet. And this thing, which represents our atoms, is a little magnet. And it's been arranged so that the big magnet is pushing up on the little magnet. Did you ever try this when you were a kid? If you had enough magnets, you lay them out on a table, and you try to make one of the atoms float above the others? Well, that's what I've got here. This is pushing up on this little magnet, and right about here, the force that it's pushing up with is just about equal to the weight of the magnet. And so if I let go of it right here, it should float. And when I let go of it, it doesn't float. It flips over and gets attracted to the big magnet. And if you tried this when you were a kid, that's what always happens. If you do this with ordinary magnets, you can never make it work because the magnet always flips over and gets pulled down. But you learned something else when you were a child and playing with toys. You learned that if you spin a top, that the top will not fall over. And it turns out that our atoms are not just little magnets, they're little spinning magnets. So we're going to spin our magnet, and now we're going to lift it to the place where the force equals the weight. Now, it didn't quite work the way it's supposed to, and the reason it didn't work the way it was supposed to is your fault. Each one of you is putting out about 100 watts of heat. And in the time before I set this up, in the time since I set this up, the room temperature has gotten a little bit hotter, and that means that the strength of the magnet has gotten a little bit less. And so in order to compensate for that, I have to take a little weight off. So I've done that, and we'll hope that things will work well now. Okay, there we go. But you know, any magician can levitate a woman and then pass a ring around her, carefully avoiding the wires that are holding her up. You never saw a magician do this. This is the real thing. That's the toy version. Now let's go back to the let's go back to the PowerPoint. So that was the toy version. Now we have the real thing. Here is a movie of trapped atoms. So what we have here is a cloud of cesium atoms, a couple of millimeters across. So that's the size across here when we get a new cloud here. Okay, so this is about 2 millimeters across at a temperature of about 1/1000th of a degree above absolute zero. And just like the top, it moves around a little bit in the trap because it was put in a little bit off center. And as time goes on, the background gas of the imperfect vacuum knocks the atoms out, and that's why the atoms go away after a certain amount of time. Now, having the atoms in the trap, we can use another trick to make the atoms even colder. And that trick is called evaporation, and it works just the way you think it should. When your coffee is too hot, you blow on it. And what is happening is that the most energetic water molecules are leaving the coffee, and what's left behind has a lower energy and therefore a lower temperature. We do exactly the same things, holding our atoms in a magnetic trap. We allow the most energetic ones of those atoms to leave, and what's left behind has a lower energy and therefore gets colder. And by doing this, we were able, and when I say we, I mean the community, because it wasn't our group that did this, have been able to achieve one of Einstein's strangest ideas. Einstein predicted in about 1924, building on the work of Satyendra Bose, that if you had a gas of atoms, like a gas of sodium atoms or rubidium atoms or cesium atoms, and if you got it cold enough, something wonderful and strange would happen. A large fraction of the atoms would stop moving. Now, in fact, the atoms don't stop moving because of Heisenberg's uncertainty principle. Heisenberg told us that you cannot know with perfect precision both where something is and how fast it is moving. And if the atom is in a trap, you know something about where it is, so you have some uncertainty about where it is, which means there must be some uncertainty about how fast it's moving. Well, but in 1924, when Einstein did this, he didn't know about Heisenberg's uncertainty principle. Of course, when he did, he didn't like it. But today we would say that a large fraction of the atoms stop moving as much as Heisenberg's uncertainty principle allows. And 1924, it was in 1995, over 70 years after Einstein predicted this, that teams in Boulder, Colorado, in our laboratories of NIST in Boulder, Colorado, and at MIT in Cambridge, Massachusetts, achieved Bose-Einstein condensation using super cold atomic gases, first laser cooled in the ways that I've explained, and then put into magnetic traps and evaporatively cooled. And this opened up a whole new area of research, much of which is being pursued here in Innsbruck. And these are the heroes of 1995, Eric Cornell, Wolfgang Ketterle, and Carl Wyman, who made the first Bose-Einstein condensate. So now we're getting toward the end of the lecture. We've been on a sort of odyssey of getting to lower and lower temperatures. And this thermometer gives us a bit of a picture of where we have been and maybe where we're going in temperature. This is a strange thermometer. It's a logarithmic thermometer. Every tick mark on the thermometer means a factor of 10 change in the temperature. So at the top of the thermometer, we have the surface of the sun, about 6,000 degrees. It's not the hottest temperature there is, but it's pretty hot. And on this thermometer, room temperature is just a little bit cooler than the surface of the sun. In fact, liquid nitrogen. And liquid nitrogen is, for most of you, the coldest stuff you've ever seen. I mean, it boils when you pour it out on the ground. It turns rubber bands into dry twigs. It collapses balloons. It's incredibly cold. And you see, it's just a little bit colder than the surface of the sun on this temperature scale. Outer space is just a little bit colder still. The first measurements of the temperature of optical molasses at 240 microdegrees were colder compared to outer space than outer space is, the coldest natural temperature in the universe, than outer space is compared to the surface of the sun, and that was just the beginning. Subdoppler cooling got you nearly as cold compared to the original optical molasses as that was compared to outer space. And finally, in 1995, the temperature was down to 50 nanokelvin, 50 billionths of a degree above absolute zero. But that was just a start. Today, people have gotten temperatures below 500 picokelvin, half of 1 billionth of a degree above absolute zero. And it may be that in the coming decade, maybe with experiments in space, that we could go down to temperatures as low as 1 picokelvin. What can we do with temperatures that are that low? We're already making better clocks, and those clocks are already being used to synchronize the satellites of the satellite navigation system. These kinds of clocks can be used to test our fundamental understanding of nature. Was Einstein's understanding of gravity correct? For example, we can test this to a level that has never been possible before. You heard in the Vice Chancellor's introduction about quantum computers and quantum simulation, one of the things that is a very active, world-leading activity right here in Innsbruck. And more things. In fact, it may be that the young people in this audience will come up with the most wonderful applications of what to do with cold atoms. As I said, some of the most exciting work is being done here in Innsbruck. Here's Rainer Blott's group working with cold ions. Rudy Grimm's group with cold neutral atoms, and Francesco Ferlena here is one of our new scientific directors here. Here's Peter Zoller's group doing theory, guiding not only the work here in Innsbruck, but the work of experimentalists all over the world. Here's an old picture of my own group. So this is not the end, because there's always something new and wonderful and exciting to learn about these things. And in particular, if you're a student here in Innsbruck and you're wondering what you should work on, and if you thought this was kind of cool, then maybe you should get in touch with one of the people in Ikoki. And if you're looking for a research experience in the United States, we're always looking for good people. So you could come to the Joint Quantum Institute, where we're doing these kinds of things and other kinds of quantum things, and we'll be happy to talk to you about the possibility of continued research. So join the fun. Thanks very much. Thank you. Thank you very much.